Hello, everyone, and welcome to our presentation on levels of measurement. Just before we get started with the presentation today, I'd like to present this information in case you are interested in additional support outside of this webinar. So we do provide assistance with all aspects of the dissertation. So if you are interested in more one-on-one support, you can use the information that you see here to contact us, and we can tell you more about the types of services and assistance that we can provide. Just to give an overview of what we're going to be talking about today, this presentation is on levels of measurement as they apply to quantitative dissertation research. So first, we'll briefly talk about what levels of measurement are and why they're important. Then we'll define and talk about the basic levels of measurement, which include ratio, interval, ordinal, and nominal. And then we'll also talk about how to determine the appropriate analysis to use based on the level of measurement of your variables. Then at the end of the presentation, we'll have an opportunity for you to ask questions. So if you have a question, you can type that question into the questions section, and any questions that aren't answered over the course of the presentation, we'll have a chance to answer your questions at the end. So first, let's talk about what exactly are levels of measurement and why they are important to know about when you're conducting your research. So levels of measurement are the properties of values or categories that appear in data for the variables that you are looking at. So for instance, let's take a variable like gender. So if you are studying gender as part of your research, you might have gender as a variable. That variable might have a certain range of values that it can take on. So people could be either male, female, or another category of gender. And so those categories would essentially be the categories or values that can appear in the data for the variable of gender. And if you're doing some kind of quantitative analysis, maybe for the purposes of the analysis, you assign numerical values to those categories of gender, like maybe you code males as a 1 and females as a 2 and another gender as a 3 and so on. And the levels of measurement kind of define how we can deal with those values or categories, or what we can do with them, or how we can analyze them. And so levels of measurement are important because they help us determine the most appropriate ways to describe, analyze, and interpret the data. And there are 4 basic levels of measurement. This is the most common classification, especially for the purposes of dissertation level research. And the 4 basic levels are ratio, interval, ordinal, and nominal. And it's important to note that although these 4 basic levels are usually what you would need to know for the purposes of something like dissertation research, you usually don't have to go beyond this. But it's important to know that there are other classifications of levels of measurement that exist. It's not that these 4 basic levels are the only classification, because there are other classifications that go beyond these levels. For instance, there are classifications that may consider count data as a separate level of measurement. But usually the 4 basic levels of measurement are what you would typically work with for the purposes of dissertation research. And that is what we will be discussing in this presentation today. But it is possible, if you're doing more advanced research, that you may need to consider levels of measurement beyond the 4 basic levels. So now let's talk about the different levels of measurement and talk about what they are and what their properties are. So the first is ratio, and interval. And this is the level of measurement that you would usually think of when you're thinking about quantitative data, because ratio and interval measures represent continuous numerical values. So in terms of ratio and interval, these might be things like, someone's age in years, or their income in dollar amount, things like that. So continuous variables. And there's a very subtle difference between ratio and interval that's important to distinguish. So ratio would be numerical values that have a meaningful or non-arbitrary 0 point. And these may include things like someone's age, their income, their height, their weight, or counts of something like, for instance, the number of people that live in a city or an area, for instance. And what we mean by a meaningful non-arbitrary 0 is that for ratio levels of measurement, 0 means that there is a complete absence of something. So for instance, if you're looking at a count of, say, people, like the number of people in an area or a city, 0 would mean that there are no people living in that city. Similarly, with something like income, if someone has an income of $0, it means they have no income at all. This is different from interval measures, because interval measures do not have a meaningful 0 point. The 0 point for an interval measure is often arbitrary. And this may include things such as temperature in Celsius or Fahrenheit, dates or years, and things like scale scores or composite measures from survey instruments. And so what do we mean by an arbitrary 0 point? This means that the 0 point for an interval level of measurement does not necessarily mean the complete absence of something. So an example of this would be with temperature. So if something has a temperature, like the outdoor air temperature, for instance, if the air temperature is 0 degrees Fahrenheit, that doesn't mean that there is a complete absence of temperature. That's just the 0 point on that temperature scale. Similarly, if we look at something like dates, for instance, the year 0 does not represent the beginning of time. It's just the 0 point for the calendar that we use, and so on. So that's what we mean, and that's how we distinguish those two levels of measurement, ratio and interval. With ratio and interval levels of measurement, an important property of this level of measurement is that the degree of difference between values is known and consistent. So for instance, let's take something like someone's age in years. We know that someone who is 11 years old is exactly 1 year older than someone who is 10 years old. And we know that someone who is 12 years old is exactly 1 year older than someone who is 11 years old, and so on. So the difference between those three ages, 10, 11, and 12, the difference between those values is consistent, and it is known and quantifiable. And this means that we can apply certain mathematical operations to these values. For ratio level data, virtually all mathematical operations can be applied. So you can add, subtract, multiply, and divide. For interval levels of measurement, you may only be able to meaningfully conduct addition or subtraction. You can't always meaningfully multiply or divide interval levels of measurement. And so what do we mean by this? So this means that for something like ratio level data, if we have something like income, for instance, say we have one person with an income of $10,000 and another person with an income of $20,000, we know that the person with an income of $20,000 has double or twice as much income as the person that has $10,000. So that would be a case where we can do multiplication. Division also applies. So we know that the person with $10,000 has half as much income as the person with $20,000. And we can also do addition and subtraction. So we know that the person who has an income of 20,000 has an income of 10,000 more than the person with 10,000. So we can add and subtract those numbers. With interval, we can't necessarily meaningfully multiply or divide all of the time. So take something like temperature, for instance. With temperature, say we have two values for temperature degrees in Fahrenheit, for instance, let's say like 30 degrees versus 60 degrees. We know that 60 degrees is 30 degrees warmer than 30 degrees, but we can't necessarily say that 60 degrees is twice as warm or twice as hot as 30 degrees. Similarly, we can't say that 30 degrees is half as hot as 60 degrees. It doesn't really make sense for us to apply those mathematical operations or transformations. So that's what we mean in terms of the mathematical operations that can be applied to these data. So now let's talk about ordinal levels of measurement. So this would be kind of the next classification of levels of measurement after interval and ratio, whereas ordinal measures represent categories that can be ranked or ordered, for instance, from lowest to highest or from highest to lowest. So this is a little different from what we think about in terms of like continuous variables or numerical data. These are more like categorical variables, but we can order these categories in a meaningful way. So examples of ordinal data may include things like education. So we can rank categories of education from lowest to highest. So for instance, we can, if we have 3 categories for education, like high school, college, and graduate school, we can rank those in order because we know that out of those 3, high school would be the lowest level of education, college would be the next highest level of education, and graduate school would be the highest level of education of those 3. The same thing with letter grade. They're categories like A, B, C, D, and F, but we can rank them in order. We know that A is the best or the highest letter grade that we can get. We know that B is the next highest, and then C and D, and so on. This also applies to individual Likert items. So if you have an item on a survey that people rate from strongly disagree to strongly agree, for instance, and maybe they rate that on a 5-point scale, these are technically categories, but we can rate them in order. So we know that, for instance, strongly disagree is a lower rating than just disagree. We know that agree is a higher rating than disagree, and we know that strongly agree is a higher rating than just agree. So we can put those categories in a meaningful order. Importantly, with ordinal data, and this is what really differentiates it from ratio or interval data, is that the degree of difference between categories is unknown or it's inconsistent or both. So we can think of this in terms of something like education. So if we take our 3 categories for education, this example, high school, college, and graduate school, we know that we can put these in order. We know that high school is the lowest, the next highest is college, and then the highest is graduate school, but we don't really know about the differences between those categories or what the distance is between high school and college compared to college and graduate school. So we can't really say that, for instance, the difference between a high school education and a college education is the same as the difference between a college education and graduate school. We can't really say or quantify those steps in between. So all we know is that those categories can be ranked in that order, but we don't really know or can't really quantify the distance between those categories in a consistent way. And because of this, we can't apply basic mathematical operations to these data. So we can't really meaningfully multiply or divide values of ordinal data. And in a lot of cases, we can't even meaningfully add or subtract these either. And the final level of measurement is nominal. And this is similar to ordinal in that we're dealing with categorical data. But for nominal data, we cannot rank or order these categories in any meaningful way. So nominal data would include things like gender. So you might have categories of male, female, and other categories of gender. It may include things like race and ethnicity. It can include things like location, region, or nationality. Other examples would be something like occupation or specialty. So like different occupations like doctor, teacher, police officer, things like that. These are different categories that people can fall into, but we can't order these categories in any meaningful way. So for instance, with gender, we may have, 3 basic categories of gender: male, female, and other, for the purposes of our study, but we can't necessarily rank those in any meaningful order, even if we were to assign numerical values to these categories. So we can't say, for instance, that male is higher or lower than female, and we can't say that male and female are higher or lower than other, even if we were to assign those with values of like 1, 2, and 3, for instance. So we can't meaningfully order or rank those categories. And so with nominal data, categories can't meaningfully be ordered, and the degrees of difference between the categories cannot be determined. And similar to ordinal data, we can't apply any meaningful mathematical operations to these data. And so now let's talk about a special case of Likert items. So we talked a little bit about Likert items before when we talked about ordinal data, but Likert items, especially in social science research, represent kind of a special case in how they are typically treated. So if you're not familiar with what Likert items are, Likert items would be attitudes or behaviors or other variables that are rated on some kind of a numeric scale, where different categories are assigned numbers, and you may have something like we see in this example here, like a 5-point scale that's rated from strongly disagree to strongly agree. But what is most common is that a survey instrument that is developed and validated to measure a certain variable will use multiple Likert items to measure a single variable or construct. So you might have, for instance, a psychological instrument that measures something like self-esteem or anxiety or self-efficacy. And those instruments will likely have multiple items or multiple Likert items, not just a single Likert item. So maybe you have a self-esteem inventory that consists of 10 Likert items. And when you have this situation, what researchers typically do is If you have multiple Likert items that make up a survey instrument, so for instance, 10 Likert items that make up a measure of self-esteem, we usually treat these measures as intervals. So if you were to take a composite score of the 10 items on your self-esteem instrument, we would usually treat that resulting composite score as an interval level of measurement. However, if we were looking at just one single Likert item, so just one item from that 10 item instrument, rather than the composite of those 10 items, we would usually treat that single Likert item as ordinal. And so now let's talk about, now that we know a little bit about the levels of measurement and how they're defined, let's talk about what types of analyses we can do with different levels, with variables that are different levels of measurement. So let's start with the different descriptive statistics that we can perform on data of different levels of measurement. So if we're dealing with ratio or interval level variables, there are a lot of different descriptive statistics that we can produce for that. So we can compute means, standard deviations, medians, which is the middle value if you were to rank the observations in order from lowest to highest. The mode, which is the most common value among the observations. The minimum value, the maximum value, as well as skewness and kurtosis, which are statistics that measure the shape of a distribution of a variable. So those are all statistics that we can produce from ratio or interval levels of measurement. For ordinal levels of measurement, we can produce frequencies, which would just be the count of how often a category occurs in the data. We can also, like ratio and interval, meaningfully produce a median. So if we ordered the observations of the categories from lowest to highest, what is the middle value among those observations? We can also report the mode, or the most common category, as well as the minimum and the maximum categories. So the lowest level category observed in the data and the highest level category observed in the data. So those are all things that we can compute from ordinal levels of measurement. With nominal data, you're more limited in what you can do. With nominal data, you can basically only meaningfully report frequencies and maybe the mode, which again would be the most common category observed in the data. So now let's talk about inferential analysis. And usually when you're doing an inferential analysis, like something like a t-test or an ANOVA or correlations or anything like that, regressions, the main determinant of what analysis you can do often hinges on the dependent variable. So the level of measurement of the dependent variable is going to be the main determinant of what analysis is going to be most appropriate. So let's talk about analyses we can do when our dependent variable is either a ratio or interval level of measurement. When the dependent variable is ratio or interval, we can use t-tests and analysis of variance to compare groups or repeated measurements of a variable. So for instance, if we wanted to see if there's a difference between two groups on some interval or ratio level dependent variable, like say for instance, we wanted to compare the income levels of men and women, and income is just represented as a ratio level variable in dollar amount, then we could use something like a t-test to do that comparison. We could also use something like an ANOVA if we were to compare more than two groups on that ratio or interval level variable. If we are looking at relationships between ratio or interval level variables, we can use Pearson correlations. So if we want to see the relationship between two variables and both of the variables are either a ratio or an interval level of measurement, you can use a Pearson correlation to examine that relationship. And then if we want to do some kind of prediction, so if we want to predict the values of a ratio or interval level variable from multiple predictors, then you can use linear regression. We can use linear regression when the outcome or criterion variable is a ratio or interval level of measurement. And linear regression can be used with predictors that are any level of measurement. So it's mainly the criterion or dependent variable in that linear regression that determines the type of analysis that we can do. So now let's move on to what we can do if our dependent variable is ordinal. So if the dependent variable is ordinal, instead of doing something like a t-test or an ANOVA, if we want to compare groups on an ordinal variable, we would do non-parametric difference tests. So we would do something like a Mann-Whitney test or a Wilcoxon test if we are doing the non-parametric version of a t-test, or a Crux-Skull-Wallace test or a Friedman test if we're doing the non-parametric version of an ANOVA. If we're looking at relationships between two variables, if those two variables are ordinal, or even if just one of the variables is ordinal, then we would do the non-parametric version of the Pearson correlation, which is the Spearman correlation. And then if we want to look at predictions, so if we want to do some kind of regression, if our dependent variable or our criterion variable is ordinal, then we would do an ordinal logistic regression. And again, for a regression, the predictors can be any level of measurement, but the outcome or criterion variable determines the type of regression that we can do. And finally, let's talk about what we can do when our dependent variable is nominal. So if we want to see the relationship between two nominal variables, so we don't have any variables that are ratio, interval, or ordinal, all of our variables are purely nominal. If you want to see the relationships between those variables, we can do chi-square tests of independence. If we want to look at prediction, so predicting membership of a category or in a category of a nominal variable from multiple predictors, then we would have to use something like a binary logistic regression or a multinomial logistic regression. The binary logistic regression we would use if there are only two categories of our dependent variable. And then the multinomial logistic regression would be used if there are more than two categories. And again, the predictors in these regressions can be any level of measurement, but we have to use these regressions when our dependent variables are nominal. So that brings us to the end of our presentation on levels of measurement. Again, if you're interested in additional support outside of these webinars, you can use the information that you see here to contact us and learn more about the different types of assistance that we can provide. But now I'll open things up to questions. So if you do have a question, you can go ahead and type your question into the question section now, and I will do my best to answer your questions. It doesn't look like there are any questions submitted yet, but I'll give a minute or two for anyone who has a question to submit one. One question is explain a paired test. So I think you maybe mean a paired t-test, or an analysis with paired data would mean that you are measuring the same variable at multiple points in time. So for instance, if you're doing like a pre-test and a post-test, say you are looking at an outcome, a single outcome, but you're measuring, participants before and after, an intervention, or before and after, some amount of time has passed, and you want to see if there's a change on the pre and the post test. That would be an example where you use, paired t-test, and you would do that if your outcome was an interval or ratio level of measurement. It's not a paired test is, I'll note that it's not only or not exclusively used if you're looking at measurements over different periods of time. It can also be used if you have measurements that are matched or can be matched in some other way. So for instance, if one example is if you're doing like a study on siblings, for instance, if your data have, if you're collecting data from each person, for example, in a sibling pair, like two brothers or brother and sister and so on, and you can match their scores together by virtue of those people being related to each other. You can also do paired tests on in those situations. Another question is, can t-test and ANOVA be used together, and what is the difference between these? So a t-test is basically a special case of the ANOVA in which you're only comparing two groups or two measurements. So a t-test would be used, for instance, if you are only comparing two groups like males and females, or only comparing two measurements like pre-test and post-test. And ANOVA would be used if you have more than two groups or more than two measurements. So for instance, an ANOVA could be used if you have more than two groups of gender. So if you're comparing like males, females, and other groups of gender. So if you had three or more groups, you would use an ANOVA for that. Similarly, you could use a repeated measures ANOVA if you have more than two measurements. So if you had like a baseline measurement, a post-test measurement, and like several post-test measurements. So maybe one post-test is at 1 month, another post-test is at 2 months, and so on. So if you have more than two repeated measurements, then you could use a repeated measures ANOVA for that. And the question about what section or phase would this content fall under. So this presentation is mainly geared towards quantitative analysis. So if you're doing quantitative research, it could apply to preparation for your quantitative methodology. So deciding what variables that you are trying to look at, what analyses you're trying to do, and quantitative analysis as well. So it applies to those areas. And in terms of the costs and timelines for support that we provide, you would have to use the information that you see here to contact us to learn more about the costs and those types of things. And to go back to the discussion about the t-test, another question was, it's an independent samples t-test used when there are different groups of people. That is correct. It's called independent because the measurements that we're comparing come from independent or different measurements. And then the paired t-test, which is also sometimes called the dependent samples t-test, is used when the data can be matched. All right, another question is, let's consider a researcher who's working on corporate social responsibility variables obtained from World Bank database. We're looking at variables like labor force, carbon emission, population density. And you're saying you're using a z-score on the variables to describe their impact on the environment. What other methods can we use to score the variables? So in z-scores would be a way to standardize values of a variables, so they're all kind of on the same scale when you analyze them. So the z-scores would kind of convert everything so that they can be interpreted in terms of standard deviations from the mean for a variable, which can help in interpretation when you're doing your analysis. Other methods to score variables would really depend on exactly what variables you're looking at. I mean, if you're just looking at continuous variables, so things like interval and ratio levels of measurement, you may consider things like transformations to those variables, because sometimes those variables could have skewed distributions. So if you're looking at something like income, for instance, or maybe even something like population density, to go off of the examples that you listed, if those variables are highly skewed, sometimes researchers will look at not just the raw variable value, but maybe a log transformed version of that variable. So that may be another way to use that variable in an analysis. So if anyone else has any additional questions, you can enter those questions into the question section now. Okay, it doesn't look like there are any additional questions coming in, so I'll go ahead and end the presentation there for today. Thanks everyone for attending. Again, if you are interested in additional support outside of our webinars, you can use the information on the screen to contact us and learn more about how we can help you. We also have, webinars on other topics that you're free to look at to see what other presentations and other topics we are covering in our webinars. But again, thanks everyone for attending today. I hope everyone found this presentation useful, and I hope everyone has a great day.